Hello, everybody. So this short lecture is accompanies section 1.2 of the lecture notes, which is about the formal definition of a group. So at this stage, we've seen lots of examples of various gadgets that I claim are groups. What we're going to do here is just formalize the definition by extracting the properties that these things share and giving a definition that can then apply to any particular context. So in case you're kind of puzzled by this approach, it is an abstraction. The purpose of it might not be kind of immediately clear. So, until you've internalized it, it can look a little bit contrived and a little bit sort of fussy. But the power of this abstract approach to algebra is that you have these descriptions that apply universally to so many different things, which are ubiquitous in mathematics, things like the integers, the rational numbers, the various sets of matrices, permutations, and so on. And this language, this abstract language of group theory, becomes extremely powerful once you have a sort of fluency in it that you can see how it applies to different contexts. So I suppose my advice in terms of thinking about this definition and learning about it would be to think about it in the context of the various examples that we know about, and maybe more examples that you might like to think about yourself. So the definition of a group, this is the most important thing probably in our entire module in terms of a piece of knowledge. So a group, G, is a non-empty set, so it's got to have at least some elements, equipped with a binary operation which we've called star, in which the following axioms hold. So we'll come back to each of these items one by one in the next few slides. So in particular, we'll come back to what it means to say that the set is equipped with a binary operation. The axioms that must hold in order for our object to be classified as a group are these three things. First of all, the operation star must be an associative operation. And what that means is that if you take any three elements of the group and write them down in order X, Y, Z, so order here on both sides of this equation is the same, X, Y, Z. Star is a binary operation. That means it's a way of putting together pairs of things. Think of addition or multiplication. If you want to star X with Y and then with Z, here think of the star as being addition or something like that. There are kind of, and you're only allowed to star sort of two things at a time. There are two ways to do this. You can star the X with Y first. The result of that process is something that's in your group G. You can star that with Z, or you can star the Y with Z first. That thing is an element of your group, and then you can star that with X. And remember, in both sides here, the overall relative order of X, Y, and Z is unchanged. What you care about is which of the two consecutive pairs, X, Y, or Y, Z, you do first. So if those two approaches give you the same outcome for all elements, X, Y, and Z in the group, then the operation is associative. And we insist that an operation on a group must be associative. We'll come back again shortly to some more comments on that. Okay, second thing, some element of G, some element in the set must be an identity element for star. That means that for every element X of G, the effect of starring it with this identity, either on the left or on the right, is to leave it alone. So whether you take any X, star it with the identity on the left or on the right, the effect of either of those things always is just X itself. So this element, the identity element, has a neutral property with respect to the star operation. And then the third thing, and this is something that we can only talk about once we have an identity element, is that for every element of the group, it should have an inverse with respect to the star operation. And again, we'll come back in a few slides to what that means, but it means that when you star the element with its own inverse, the result of that should be this identity element that has been mentioned in item 2 here. So that's the definition of a group. Okay, it's abstract, it's formal, but it's very highly applicable to so many situations that we know about in mathematics and that we've seen even in the first section of these lecture notes. So the power of it is that it kind of pulls together all these superficially different things that actually at the level of their algebraic structure have a lot of properties in common. So just to kind of go over it, I suppose we do need to all be familiar with this formal definition and be able to work with it in a fairly sort of accessible and fluent way. If that doesn't come to you immediately, definitely don't worry. It's something that takes a little bit of time to get used to. So, but to just kind of recap on a few of the elements of that statement and what they mean. But first of all, to say that a set is equipped with a binary operation, okay, there's some meaning hidden into that sort of concise statement that needs to be, that we should be aware of and that we should highlight. So a binary operation is a way of combining two elements of the set to produce a new element still in the set. So technically, it's a function from the set of ordered pairs of elements. This G cross G means the set of all pairs of the form XY, where X and Y are both elements of G. So technically, a binary operation is a function from that thing associated to every ordered pair it gives you back an element of G. So think of addition. You give it two things, it gives you back one thing. Okay, so addition is a binary operation on the set of natural numbers. Subtraction is not. And you can think about why it's not. So remember, the set of natural numbers is a set of all positive integers, 1, 2, 3, 4. To say that addition is a binary operation on that set means that you can take any two elements of that set, add them, and you're still within that set. Then you can ask yourself, is the same as true of subtraction if you think of it as a binary operation on the set of natural numbers? Subtraction is a binary operation on the set of all integers, but not on the set of natural numbers. And these are the sort of subtle, fussy points that really kind of are worth thinking about if you want to get a clear understanding of what we're talking about here. Okay, so matrix multiplication is a binary operation on the set M3Q of all 3 by 3 matrices whose entries are rational numbers. Okay. That's what that statement is saying, is that if we take any two 3 by 3 matrices whose entries are rational numbers, we can multiply them together using the machinery of matrix multiplication, and the result of that will again be a 3 by 3 matrix whose entries are rational numbers. Okay, but I claim matrix multiplication is not a binary operation on the set of all square matrices with rational entries. Okay, and I'll leave it for you to think about why that is. Can you take any pair of square matrices, multiply them together using matrix multiplication? Okay, that's the question. So the other thing that I just want to mention, and if you're reading about group theory in books or on websites or anything else, you might come across this axiom of closure in addition to the 3 axioms that we've mentioned. So I just want to mention something about that. So implicit in the statement that star, or whatever it's called, is a binary operation on our set G, is the condition that when you take two elements of G and combine them with star, the outcome of that is again an element of G. And another way to say that, which algebraists like, is to say that G is closed under the operation star. What that means is that when you take two things that are in G, combine them with star, the outcome of that should still be in G. And of course, the failure of subtraction on the natural numbers to be a binary operation is for exactly that reason. If you take a pair of natural numbers, let's say 3 and 7, and if you do 3 minus 7, 3 minus 7 is a sort of sensible concept in some context, but it's not a natural number. So, trying to allow yourself to subtract any natural number from any other will take you outside of the set of natural numbers. And that's why subtraction is not a binary operation on the natural numbers. Okay, so I suppose what I'm talking about here is just the fact that these terms that appear in the definition of a group, like binary operation, they have very specific meaning, which we need to kind of be aware of and kind of incorporate somehow into our vocabulary. Okay, that's the comment on the binary operation bit. The next thing was associativity. We wanted our operation to be associative. So associativity is a property that some operations have and that some don't. Fine. So a binary operation combines elements in pairs. So think about addition. So, okay, of course you can add 5 numbers. So if I ask you to add 3 plus 5 plus 7 plus 14 plus 11, of course we can all do that. But if you're doing it mentally, what you'll probably notice, whether it's subconscious or conscious, is that, the way you do it is you kind of add them in pairs and then add the pairs together. So if you're doing 3 plus 5 plus 7, you can do 3 plus 5, that's 8 plus 7 is 15. You can do 5 plus 7 is 12 plus 3. But you kind of have to add them in pairs and then add another one on at each stage. And whether that process happens kind of subconsciously or consciously, it's really two things that get added at a time, and then you can add in more. And that's what it means to say it's a binary operation. It combines elements in pairs. And so, of course, once you have that, you can combine more than 2 elements by combining them one pair at a time and then adding in another one. The associativity property is concerned with when it matters, whether or not it matters, which pairs you put first. Okay, so operation is associative if whenever you have 3 elements, x, y, and z, combining x, y in that order first, and then with z on the right, always gives the same outcome as combining y, z first and then x on the left. So when you're thinking about this, please give some attention to the fact that on both sides of this, the 3 elements, x, y, z, appear overall in the same order. It's x first, then y, then z. You're not changing the relative order of any of the pairs. You're just talking about which of the 2 consecutive pairs you combine first. So as I said, some operations are associative, some aren't. And I think when you're learning about concepts like associativity, it's kind of hard to get an appreciation of it by looking at examples of things that are associative. It's useful to look at an example of something that isn't. And probably the most familiar example to most of us of something that's not associative is the subtraction operation on the integers. So if you want to write down 3 minus 5 minus 6, there are 2 ways to put brackets around a consecutive pair there to tell you which of those subtraction operations happens first. And they're not the same. The outcomes are not the same if you do the 3 minus 5 first and then subtract 6, and if you do 5 minus 6 first and then subtract that from 3. So that's an example of an operation that's not associative. And that means it can never be the operation on something that we would call a group. Okay. So that's associativity. The identity element or neutral element, I think this is one that we talked about last week quite a bit with the examples. An identity element is one that has really a neutral role in terms of the binary operation. So I think I like the word neutral element, as I said. Identity is more commonly used. So an identity element for a binary operation is just one that has no effect on any other element when combined with it, either on the left or right. So for example, 0 is an identity element for addition in the integers. Adding 0 to an integer has no effect. 1 is an identity element for multiplication of integers or real numbers or complex numbers or rational numbers. Multiplying by 1 has no effect. The good old 2 by 2 identity matrix has the identity or neutral property for multiplication of 2 by 2 matrices. If you multiply another matrix by this one, it has no effect on the other one, no matter what it is. Okay, so that's the concept of an identity element. And again, in order for some algebraic structure to meet the criteria for what we call a group, amongst its elements must be one which has the neutral property with respect to its operation. So of course, you can have lots of algebraic structures that don't have this property, but they're not groups. Okay, what we call a group must have that property. And then the final thing is the concept of inverses. And here again, I just want to highlight that in order to even talk about the question of whether your algebraic structure has inverses or not, you have to already have an identity element. If you don't have an identity element, the question of inverses doesn't arise. It can't even be defined. So two elements of some set that has a binary operation star are inverses of each other with respect to that operation if when you combine them with the operation, you get the identity element. And we insist as well in the definition that that has to be true whether we combine them xy or yx, which are not necessarily the same thing for every operation. For example, they're not the same thing for matrix multiplication or for subtraction. They are for addition of integers, but generally speaking, for any abstract structure, they might not be. Okay, so for example, if you're talking about the group of non-zero rational numbers under multiplication, the identity element there is 1. The inverse of any non-zero rational number is its reciprocal. So 2 over 5 and 5 over 2 are inverses of each other for multiplication of rational numbers. And a way of thinking about that, which we are familiar with from division and from using matrix inverses and so on, is that basically it means you can sort of undo the work of multiplying by 5 over 2 by multiplying by 2 over 5, which you might also call dividing by 5 over 2. So, this idea of having elements that are inverses to each other means somehow they kind of undo each other's work with respect to the operation. And again, having a sort of abstract way of describing that in terms of identity elements and abstract binary operations can be extremely useful when you want to study a wide range of different structures in different contexts where, you might not even have words like division as we do for numbers. Okay, so in a group, the binary operation must have an identity element. Every element must have an inverse, and that inverse must live within the group as well. And it's possible, of course, for an element to be its own inverse. The identity element, for example, will always be its own inverse, but it's possible for other elements also to be equal to their own inverses. Okay, so those are the various properties that a group must satisfy. And just to get back to the definition for a second, I guess this is if somebody hands you an example of an algebraic structure, some set of objects with some binary operation on them, the question of whether that thing is a group or not is the question of whether these properties are satisfied. Okay, is the operation associative? Is there an identity element in the group? Does every element have an inverse within the group? And I think a good way to get used to the definition is to just kind of practice that exercise of taking examples of algebraic structures and asking yourself, are these properties satisfied or not? And of course, if to be a group, all the properties have to be satisfied. If it's not a group, only one of them has to fail. So as soon as you've shown that one of them fails, then you're done. It's not a group. Okay, so, excuse me. So here's an example of such a task, and you'll find a few more of them in the lecture notes on section 1.2. So this particular example, this UT sub 3Q, this is the set of 3 by 3 upper triangular matrices with entries which are rational numbers. And the question is this a group under matrix multiplication? Okay, so I'm not going to completely answer the question here, but I'll sort of mention things that we would have to do, and you can have a look at the lecture notes where there are some more examples of this type. So we're talking about the set of 3 by 3 upper triangular matrices whose entries are rational numbers. The question is it a group under matrix multiplication? So first of all, to recall, a square matrix is upper triangular if all the entries below its main diagonal are zeros. So the main diagonal runs from the top left to the lower right. So we're saying that the elements in the lower left region, the lower left triangle there with 3 entries, they must all be 0 to be an upper triangular matrix. So to answer the question, you must ask yourself these, of whether it's a group, you must ask yourself these questions. You know, is it true, first of all, that this set is closed under the operation of matrix multiplication? If we take 2 3x3 upper triangular matrices and multiply them, is the outcome of that still upper triangular? And the answer to that is, you know, decided by looking at the mechanics of matrix multiplication, just deciding if you take 2 3x3 matrices that both have a little triangle of zeros in the lower left, 3 entries in the lower left, and if you multiply them together, do you retain that property? Okay. So it's the operation associative. Okay. Something that is not completely obvious, but which is true, and I won't ask you to sort of go through the steps of verifying it, is that matrix multiplication is an associative operation. So if it's an associative operation on the set of all 3x3 matrices, then it's certainly an associative operation on some subset of that. So yeah, so matrix multiplication is associative. That one is satisfied. And a way of seeing that is that matrix multiplication, of course, matrices, as you know, represent linear transformations. And matrix multiplication represents composition of linear transformations. Composition of functions is always an associative operation. And so that's one way to see how matrix multiplication must be associative. Okay, third question, does this set contain an identity element for matrix multiplication? Okay, and kind of the go-to thing there is to look at, well, the 3x3 matrix identity. Is that an upper triangular matrix? So is it in our set? If it is, then it's an identity element within that set. And then the final question is, does every element of the set that we're talking about here have an inverse that also belongs to that set? Okay, and here again, you have to think carefully. We're talking about inverses for matrix multiplication. So there are 2 questions. Does every upper triangular matrix have an inverse for matrix multiplication? And if so, is that thing also an upper triangular matrix? Okay, so you might find that the answer to the first part of that maybe is no. Then you could ask, is there a version of this question that we could ask? You know, instead of taking all the 3x3 upper triangular matrices, if we were only to take the ones that do have inverses, would that be a group under matrix multiplication? Okay, and then you can think again about these questions and ask yourself, well, are all the properties satisfied? Okay, that's an example. You'll find some more examples in the lecture notes, and we can certainly have a look at a few more in workshops on that, and there'll be some of the first homework as well, which is coming soon. But you know, these are the sort of questions we have to ask to think about whether something is a group. If it's not a group, it could be some other type of algebraic structure that people are interested in studying, but our business in this course is to study groups. So the answer here is no, and I'll let you think about the reason for that, and please follow up with me if you're not clear on it. But maybe there's some adaptation that we could make to this thing to make it into a group. That's something that you could think about. Okay, that's the key content on the definition of a group. There's a bit more detail in section 1.2 of the lecture notes. And there's something in particular that I'd like to highlight, which is towards the end of that section in the lecture notes. And something you might have already thought about. So we've noticed so far in our first section of notes, that we've had some examples of groups that are infinite sets. For example, the integers with addition, the non-zero complex numbers with multiplication. We've had some examples that are finite sets, such as groups of symmetries of a triangle, such as groups of permutations, such as that example of the 4 complex fourth roots of unity. So groups can be either finite or infinite. And that's one sort of dichotomy in the subject of group theory. You can study finite groups or you can study infinite groups. Both are very interesting. The same definition applies to both for a group. There are things you can do with finite groups that you can't do with infinite groups. For example, you can count their elements. You can look at sort of different types of, you can use different sort of combinatorial approaches involving things like counting, kind of features of discrete maths. There are other groups that are infinite and they kind of have more like the features of continuous mathematics, where their actual groups might also sort of have some continuous functions defined on them, for example, like the group of complex numbers of non-zero complex numbers under multiplication, like groups of functions and real numbers, these sorts of things. So there's quite a lot of variation in group theory between the realms of the sort of finite and infinite, between the discrete and the continuous as well. And the other sort of dichotomy that exists within the subject that I just mentioned is, we haven't talked about, so if we go back to the properties of group, the axioms of a group, there's no mention here with our operation of whether it must be true for any pair of elements x and y, that x star with y should always be the same as y star x. Okay, if that is always the same, then the group, the operation, in addition to having the associative property, also has the so-called commutative property. Okay, groups can either be commutative or not. And we've seen examples of both. For example, with the integers under addition, addition is a commutative operation on the integers. A plus b is always the same as b plus a. But with the groups that we've seen, for example, of matrices under multiplication, matrix multiplication generally is not commutative. For a pair even of 2 by 2 matrices A and B, AB is generally not the same thing as BA. It happens occasionally, but it usually doesn't. And so that's an example of a non-commutative group. And the other sort of dichotomy in the subject is between commutative groups and non-commutative groups. This is all mentioned in the last part of section 1.2 of the notes, so have a look at it there. But the word for commutative in group theory is Abelian, and that word is there in those notes. So have a look at that and have a think about it. So people classify groups either as Abelian or as non-Abelian, which means the operation is either commutative or not. And again, the study of Abelian groups and the study of non-Abelian groups have sort of evolved into separate things. Abelian groups are sort of somehow easier to deal with because, of course, operations where everything commutes are easier to manage than operations where they don't. It's a very strong property for an operation to have. Okay, our challenge for this particular video lecture is similar to that example about the upper triangular matrices. We have an operation here denoted by star, which is defined as a set of positive rational numbers. So remember, rational numbers are fractions involving integers. Positive means not 0 and not negative. So 2 over 5, 17 over 23, things like that are in this set. And the operation star is defined in this way, that the star of A with B is the ordinary product AB divided by 2. So star is very like ordinary multiplication, except it also divides by 2. So for example, with this operation, 3 star 4 would be 12 over 2, it would be 6. Okay, and this operation is defined for all positive rational numbers A and B. And your challenge is to determine, with explanation, whether or not the set of positive rational numbers is a group under this operation, and to give some explanation of your answer that will be shareable with the class. And again, this week, either handwritten or typed answers are very welcome. We'll start talking a little bit this week also about a bit of typesetting, so we can think about how to do a sort of slide type presentation if you wanted to. So that's the challenge. I don't think it's an easy challenge, and I think to give a complete answer to it we'll take a little bit of careful thought and careful organizing as well in terms of how it's written. So thank you everybody very much, and that's it for this one. We'll see you later in the week. Good luck.